Hello everyone, I am Dr. M. Laxmidevi, Associate Professor in the Department of Electrical and Electronics Engineering. Uh, Welcome to the course Electrical Measurements and Instrumentation. Today's topic is extension of range of ammeter and voltmeter. Uh, First, let us see range extension of ammeter. So, we are talking about PMMC type instruments. So, PMMC instrument, we have seen that it is a permanent magnet moving coil instrument. So where you have a permanent magnet and moving coil, the current which is to be measured is fed to the coil with the help of the springs. So here we know that there are springs here. So with the help of these springs, current is fed into the coil. So inside here you may have a coil placed. So what happens is these springs, they are unable to carry springs have limited current carrying capacity. So therefore we can use these instruments only for measuring current up to 20 milliamperes. So above that, if you want to measure the current, so for current above 20 milliamperes, we have to connect a resistor as shown in the diagram here. We have to connect a resistor. This is called as shunt. So it is connected in parallel with this PMMC instrument. Its value, it is made up of manganese. For DC it is made up of manganese, and for AC it is made up of constant N. So coming to this diagram, let us see. Rm is the internal resistance of the movement. Then RSH is resistance of the shunt. Im or IFS is the full scale deflection current of the meter in amperes. ISH is shunt current in amperes, and I is the current which needs to be measured. So let us derive the equation. So from this diagram we can say that ISH is equal to, so this current can be written, shunt current can be written in terms of I and the meter current I minus Im. So we have this relation ISH into RSH is equal to Im into Rm. So from this we can write RSH is equal to Im into Rm by ISH. So from this relation RSH is equal to Im Rm divided by RSH. From this we can write Im into Rm by I minus Im. ISH is equal to I minus Im. Therefore, RSH can be written as Rm by N minus 1, where M is equal to, we can write M is equal to I by Im. So this M is called as multiplying factor or multiplying power of the shunt. So it is defined as the ratio of total current to the current through the coil. So from this we can write, from this relation we can write M is equal to, from this we can write M is equal to M minus 1 is equal to Rm by RSH. So from this M is equal to Rm by RSH plus 1. So this is the other relation which you can write for M. So M is called the multiplying factor of the shunt, and it is defined as the ratio of total current to the current through the coil. So in this way, we can extend the range of PMMC instrument. So initially, PMMC instrument can be used for measuring currents up to 20 milliamperes. So with this arrangement, by using shunt, so shunt is a low resistance value which is connected in parallel with the meter. By using this arrangement, we can extend its range up to 50 amperes. So some of the important properties of shunt are, let us see the properties of shunt or the requirements for a resistor to be connected in shunt. So its properties are, its resistance, shunt resistance, should not vary with time. And also another important property is the resistance should have low the resistor should have low temperature coefficient. Shunt resistor should have low temperature coefficient. So these are some of the important properties of a resistor for it to be connected in shunt to extend the range of ammeter. So it is made up of, so therefore it is made up of manganese for DC measurements, and for AC measurements the material used is constant N. So here, as you can see, coming to the meter, we have a resistor connected in shunt. So this is called as shunt resistor. This is called as shunt. Suppose we want to measure the current I. So the current which can flow through the meter is only 20 milliamperes. The remaining current has to flow through the shunt. So in this way, by measuring, we can measure the current. So this shunt is made up of low resistance value. So this copper, this is a moving coil. So it is made up of copper, whereas the shunt is made up of manganese. So due to the difference in the uh, materials used, so therefore an error will be occurring. So in order to avoid these errors, what we do is we connect a resistor called as swamping resistance. So this resistance is called as swamping resistor. So since these two are made up of different materials, so the temperature coefficients will be different. So change in temperature will have different effect on these two resistances. So therefore, in order to avoid that, we connect a resistor called as swamping resistor. Now let us see some of the problems. A PMMC meter has meter resistance of 100 ohms and measures maximum current of 10 milliamperes. Find the shunt resistance for measuring 100 milliamperes. So now here what is given here is the given data is meter resistance, that is Rm is equal to 100 ohms and measures maximum current of 10 milliamperes. So that means Im is equal to 10 milliamperes. Find the shunt resistance RSH we need to find for measuring 100 amperes. So actually this is the full scale current or meter current 10 milliamperes. We need to extend its range to 100 milliamperes. So what we do, we have to find out the value of the shunt resistance. So according to the formula, so we have RSH is equal to Rm by M minus 1. So where M is the multiplying factor or multiplying power, so we define it as I by Im, where I is the total current 100 milliamperes and Im is 10 milliamperes. So from this is equal to 10. So M is equal to 10. So we can substitute in this formula. So Rm will be equal, what is Rm? Rm is equal to 100 divided by, this is 10 minus 1. So which is equal to 100 by 9. So 100 by 9 is equal to 11.11. So this is the answer. So resistance which we need to connect is 11.11. So this is the value of shunt resistance. Now, so this is the case. Till now we have seen the case for extending the ammeter range to a single value. So now let us see. So this is an example of multi-range. This is the circuit for multi-range ammeter. So in order to measure, suppose we have more than one current. Suppose there are a number of currents to be measured, I1, I2, I3, I4 of different ranges. So in order to measure these different ranges, so we have this arrangement or setup called as multi-range ammeter. Here, as you can see here, so there are different values of resistors to be connected in parallel with this meter. So that when you connect this is actually it should be RS1, RSH1, this is RSH2, this is RSH3, this is RSH4, and so on. So depending upon how many values you need to measure, so those many shunts need to be connected in parallel with the meter. So with this we can extend its range to 4. With this circuit arrangement we can find 4 different current value. We can extend 4 different current ranges. So same formula we can apply. RSH1 is equal to, so Rm divided by M1 minus 1. So Rm is meter resistance, so this will remain constant. Whereas coming to this multiplying factor, so this will depend upon the current total. So this is equal to, M1 is equal to I1 divided by Im. Next, RSH2 is equal to Rm divided by M2 minus 1, where M2 is equal to I2 by Im. Similarly, and so on, we can find out for all the resistors. So RSH3 is equal to, and this is RSH4 is equal to Rm into divided by M3 minus 1. Here M3 is equal to I by I3 by Im, and here you have M4 is equal to I3 by I4 by Im. So in this way, we can extend the range of extend the range of ammeter to find out to measure different current ranges. Next is, we'll solve an example based on this. Design a multi-range DC milliammeter with a basic meter having an internal resistance of 50. So its resistance is 50, and full scale deflection current Im is equal to 1 milliamperes. The required ranges are 0 to 10 milliamperes, so 0 to 50 milliamperes, 0 to 100, and 0 to 500. So we need to construct a multi-range ammeter where we need to extend the range to 4 different values. I1 is equal to 10 milliamperes, I2 is equal to 50 milliamperes, I3 is equal to 100 milliamperes, I4 is equal to 500 milliamperes. So in order to find out I1, we need to find out RSH1. To find out, we need to find out RSH3 and RSH4. So these are the different values we need to find. So by using the formula, RSH1 is equal to Rm by M minus 1. Here M1 is, first find out M1. So M1 is equal to I1 by M. So I1 is equal to 10 milliamperes. So that is what written here. I1 10 divided by M, 10 divided by 1. So that is equal to 1. So a multiplying factor is equal to 10. Next, RSH1 is equal to, so Rm divided by this M1 minus 1. M1 minus 1, 10 minus 1, that is equal to 9. So 50 divided by 9 is equal to 5.55. So this is the RSH1 which need to be connected across the meter, across the PMMC meter to extend its range. This is RSH1. 1 is equal to 5.55 ohms. So in order so that the current I1 is equal to 10 milliamperes can be measured. So next is RSH2. So same formula we can apply. RSH2 is equal to Rm by M2 minus 1. So here M2 is equal to I2 by Im. I2 is equal to 50. So second range is 50 milliamperes. So 50 by 1 is equal to 50. RSH2 is equal to by using this formula, 50 divided by 50 minus 1, so it comes out to be 1.02 ohms. So next is RSH3 is equal to Rm by M3 minus 1, where M3 is equal to I3 by Im. I3 is equal to, so this is the third range, 100. I3 is equal to 100 milliamperes divided by 1 is equal to 100. RSH3 is equal to 50 divided by 100 minus 1, 0.505 ohms. RSH4 is equal to Rm by M4 minus 1. Here M4 is equal to I4 by Im, that is equal to 500 divided by 1, which is equal to 500. RSH4 is equal to 50 by 500 minus 1, which is equal to 0.1 ohms. So these are the, so in order to design a multi-range ammeter to extend the, in order to design a multi-range ammeter to measure 10 milliamperes, 50 milliamperes, 100 milliamperes and 500 milliamperes. So these are the different resistors which need to be connected. So which we have found, RSH1 is 5.55, RSH2 is 1.02, RSH3 is equal to 0.505 and RSH4 is equal to 0.1 ohms. Now there are some, for the previously seen multi-range ammeter, so there are some disadvantages. So what are those? Let us see. So in order to extend the range of ammeter, in order to measure different values of currents, we need to connect different resistors. So this increases the cost of the equipment or the device, and then this is one of the disadvantage. Another disadvantage is when we are moving the switch, so there is a selector switch in order to connect these resistors to different, as you can see here. So there is a, in the previous diagram we have seen, so here is a selector switch. So with the help of the switch, we can select any one of the shunt resistor and extend its range to corresponding value. When we are changing the position of this switch, what happens is at that time ISH is equal to 0. So at that case, Im will be equal to the total current which is to be measured. So this will spoil the equipment, or this will result an error. So in order to avoid this, we have a different arrangement called as Aeronautical shunt or universal shunt. Here you can see that, so there are three different resistance values, all of them connected in series, and there are tappings provided at each point. So at the junction of R2 and R1, there is a tapping provided. At the junction of R3 and R2, there is a tapping provided, and we can select the switch. So we can select the switch as per the requirement. So we can move the switch to 1, 2 or 3. So here this is the arrangement to measure three different values of current. So by this arrangement, as you can see here, the cost of the equipment is reduced, as well as the size of the equipment is also getting reduced. Now let us see the derivation and then we'll solve the problems. So from this, here also we know that ISH into RSH is equal to Im into Rm. This is the basic circuit which we have seen, ISH. So this is having Rm, meter resistance, this is having RSH. So ISH into RSH is equal to Im into Rm. Now when the switch is at position 1, so it connects the resistor. So what happens is, this is the circuit now. So R1, this is the current I1 which need to be measured, and remaining, this will be connected in series with the meter resistance Rm. So this is how the circuit will look like. So here now the shunt resistance is RSH is equal to R1, whereas in here the meter resistance is Rn plus R2 plus R3. So at position 1, R1 is in parallel with R2, R2, R3 and Rm. So that is what written here. So therefore we can write this equation as I1 into ISH. Now ISH is, so we can write I1 into R1 is equal to Im into, now the resistance is R2, R3 and Rm, where I1 is the first range which is required. So from this we can write, when the switch is at position 2, that is in this position, R1, R2, this is R3. So now the equation will become, so if we want to measure this current I2, so I2 into, now the current will be, resistance will be R2 plus R1 is equal to Im into R3 plus Rm, and so on when the switch is at position 3. So R1, R2 and R3, these are the shunt resistors connected, and this is the meter resistance. So the corresponding equation is R1 plus R2 plus R3, so is equal to Im into Rm. This is the third range which is required. Now we'll see one problem based on Aeronautical shunt. To provide an ammeter, design an Aeronautical shunt to provide an ammeter with the current ranges 1 ampere, 5 amperes and 10 amperes. A basic meter resistance is 50 ohms and full scale deflection current is 1 milliamperes. So this is the diagram. So here we need to extend the range to three different values, 1 ampere, 5 amperes and 10 amperes. Meter resistance given as Rm is equal to 50 ohms and full scale deflection current, so that is Im is equal to 1 milliamperes. For this we need to find RSH1. This is the circuit diagram. So from this we can see that, so this is the important point which we need to remember. For higher current range, the shunt resistor should be lower. That means for higher current, that is this one. So among all the current ranges, 10 amperes is the highest one. So it requires the lowest shunt value. From the equation we have just derived. So when the switch is at position 1, so the resistance, the shunt resistance which is connected is R1 only. So this is the lowest resistance we get. So here I1 is equal to, we can write it as 10 milliamperes. So equation we can write it as I1 R1 is equal to Im into R2 plus R3 plus Rm. Accordingly, we can find out R1 value. Substitute the values which are given, I1 and Im are given, even Rm is given. So this is I1 is equal to 10 amperes. So 10 into this is equal to, Im is equal to 1 milliamperes, 10 power minus 3. So R2 and R3 we need to find. We have the value of Rm. So from this we can write, this is equal to 10 power minus 4 R2 plus R3 plus 50. So this is equation 1. So in order to find, so we have three different unknown values of shunts. So we need three different equations. So let us write the second equation. When the switch is at position 2, so in this case, we can write R1, R2 into I2 into R1 plus R2 is equal to Im into R3 plus Rm. Whatever the values are given there, we can substitute. Here I2 is equal to 5 milliamperes. So this is 5 milliamperes, 10 power minus 3. R1 plus R2 is equal to, this is 1 milliampere, R3 plus 50. From this we can write R1 plus R2 is equal to, This is 5 amperes. So this is 5. So here we will get 10 power minus 3. So R1. So R1 is equal to, so from this we got this expression. This is 5 into, so if it comes here, it will be divided by 5. So finally you will get the equation as R1 plus R2 is equal to 2 into 10 power minus 4 R3 plus 50. So this is the second equation. Now let us see the third equation. Now when the switch is at position 3, now the shunt resistance will be R1 plus R2 plus R3. So this into I3 is equal to meter resistance is Im into Rm. Meter current is Im, meter resistance is Rm. So here I3 is equal to 1 amperes. So now R1 plus R2 plus R3 is equal to, this is 10 power minus 3 into 50. So this is the third equation. So by making use of equation 1, 2 and 3, we can solve these equations to find out R1, R2 and R3. So or you can solve in this way. From this equation, we can write this equation as R1 plus R2 is equal to 0.05 minus R3, and then substitute this equation in equation 2, that is this one. So R1 plus R2 is equal to 0.05 minus R3. 0.05 minus R3 is equal to 2 into 10 power minus 4 into R3 plus 50. So we'll get an equation in R3. Solve that. You will get R3 is equal to 0.039, which is approximately equal to 0.04 ohms. So this is a value of R3. Next, find out, in order to find R2 value, we can make use of this equation. R1 plus R2 is equal to 0.05 minus R3. We have the value of R3, 0.05 minus 0.039, which is equal to 0.01. So R2 we can write it as 0.01 minus R1. Substitute this equation. Substitute the value of R2 in equation 1. So equation 1 is this one. R1 is equal to, so R1 can be written as 10 power minus 4, 0.01 minus R1 plus 0.039 plus 50. So that is R2. So this is R2, this is R3, and this is Rm. This one is R2. So from this we can find out, we got an equation. The only unknown variable here is R1. Solve this, you will get the value of R1, 0.005 ohms. Now we can make use of this relation and then substitute the value of R1. So you will get the value of R2 is also equal to 0.005 ohms. Next topic, range extension of voltmeter. Now let us see how to extend the range of voltmeter, PMMC type instrument, which can be used as a voltmeter. So PMMC instrument can be used as a voltmeter also to measure voltage. So with this, it can measure only up to 100 millivolts. But when you extend, so in order to extend its range, to extend the range of voltmeter, so this is the arrangement. We connect a series resistance called as multiplier. This is called as multiplier. in series with the meter. So meter resistance is Rm and meter current is Im. So here series resistance is called as multiplier. Function of the multiplier is to limit the current through the basic meter so that the meter current does not exceed the full scale value. So here in this diagram, so Im is the full scale deflection current. So it is also denoted by IFS. Rm is the meter resistance. RSC is multiplier resistance. Vm is voltage across the meter for the current Im. So next, voltage across this is Vm, and total V is the full range voltage of the instrument. So from this diagram we can write this equation. So the voltage V is equal to, this is the full range voltage of the instrument, can be written in terms of meter current, meter resistance. So Im into, same current is flowing through both the resistances, so RSC plus Rm. From this we can find out the value of RSC. RSC is equal to V by Im minus Rm. RSC is equal to V by Im minus Rm. So this is what we have obtained. We can also obtain this formula by using this. We know that Vm is equal to voltage across the meter. Vm is equal to Im into Rm. Total voltage is equal to this Im into RSC plus Rm. So divide these two, equation 1 divided by equation 2. So you will get this equation, V by Vm is equal to Im into RSC plus Rm divided by Im into Rm. So Im is common, ISC plus Rm divided by Rm. So this is V by Vm. We can write this in the form of RSC by Rm plus this is V by Vm. So V by Vm is also equal to M, where M is nothing but the multiplying factor of the multiplier. We write it as M is equal to V by Vm. This is the full range voltage of the instrument and this is the voltage across the meter. So RSC, we can write this equation as RSC is equal to, this equation can be written as M is equal to, we can write 1 plus RSC by Rm, or M minus 1 is equal to RSC by Rm. So from this we can write RSC is equal to Rm into M minus 1. So this is the equation, RSC is equal to Rm into M minus 1. So in order to extend the range of voltmeter, so this is the series resistance which need to be connected. So let us understand this with the help of a problem. A PMMC instrument with full scale deflection of 100 microamperes. So that is, this is Im is equal to 100 microamperes and a coil resistance of 30 kilo ohms. Coil resistance means meter resistance. So this is 30 kilo ohms is to be converted into a voltmeter. Calculate the multiplier resistance. So RSC we need to find, required for the voltmeter to measure 10 volts at full scale. So voltage, full range voltages, V is equal to 10 volts it is given. We need to find out RSC. Determine the applied voltage. So let us solve this. So at 10 volts, so full range voltage of the instrument is equal to 10 volts at full scale deflection. That is, Im is equal to 100 microamperes. With this data given, RSC is equal to V by Im minus Rm. So we have the value of V, that is 10, divided by Im is equal to 100 microamperes. So micro means 10 power minus 6, minus Rm is equal to 30 kilo ohms, 10 power 3. So we get this value as 70 kilo ohms. Next part of the question is, determine the applied voltage when the instrument indicates 0.5 full scale deflection and 0.1 full scale deflection. So we have to find out the value of V here. So at when V is 0.5 times full scale deflection, so it indicates Im is full scale deflection means the current, the maximum current which can indicate. So that is, if we take it as 0.5 times, 0.5 times 100 microamperes, so that is 50 microamperes. Now the voltage range is, the voltage, full range voltage is given by V is equal to Im into Rm plus Rsc. So here Im is equal to 50 microamperes and Rm we know that Rm value is given as 30 and Rsc is equal to 70. So if you solve this, we'll get the value as 5 volts. Now when voltage is 0.1 1 times of full scale deflection means that means Im is equal to 0.1 into 100 microamperes. So this comes out to be 10 microamperes. So using the same formula, V is equal to Im into Rm plus Rsc. So Im is equal to, now here Im is equal to 10 microamperes and Rsc we know it is 70 and Rm is equal to 30 kilo ohms. So this is the value of the voltage which is indicated by the voltmeter. So this is what we have obtained. Determine the applied voltage when the instrument indicates 0.5 FSD and 0.1 FSD. FSD indicates here full scale deflection. Now this is the circuit for multi-range voltmeter. So here you can see that there are a number of, so in order to extend its range to 4 different values V1, V2, V3 and V4. We have 4 different resistors connected and there is a switch here to select the different value of resistance to be connected in series with this meter. So this is the simplest circuit of multi-range voltmeter. The formula here is saying this is RSC. So RSC1 here is equal to, we have the formula Rm into M minus 1, where M1 is equal to, we can write it as V by Vm or V1 by Vm, or we have this formula also RSC1 is equal to V by Im minus, here V is equal to the voltage which need to be extended. RSC1 we can write it as V1 by Im minus Rm. RSC2 is equal to V2 by Im minus Rm and so on. So the drawbacks of the previous circuit are avoided with this arrangement or with this circuit. Here you can see that the same resistors can be used for extending its range to different values. So here we can extend its range to V1, V2, V3 and V4. So with this circuit arrangement, the cost of the resistance is decreased and also the size of the equipment is also reduced. Now let us see the equations here. With the help of this selector switch, we can select any value of resistance which need to be connected in series with this meter. So suppose we connect the switch at position 4. So at position 4, multiplier resistance will be R4. So this is the only resistance which is connected. So this is the multiplier resistance. We have this relation. So total resistance. So we can write the equation as total resistance R is equal to V by I. We know this. What is V here is V4 and I is nothing but this. And also we have total resistance is equal to, only for this circuit, when this selector switch is connected to R4 comes into picture, and here we have the meter resistance and this is R4. So for this case, total resistance is R4 plus Rm. So we can write Rm is equal to this R4, we can write it as RT is equal to R4 plus Rm. So R4 can be written as RT minus Rm. Similarly, we can write for other positions also. When the switch is at position 3, multiplier resistance is R3 plus R4. So in this way, so at position 3, V3 comes into picture. Resistance will be R3 and R4. And here you have the meter resistance. So total resistance can be written as R is equal to V by I. The current flowing here is meter Im and this is V3. Total resistance RT can be written as R3 plus R4 plus Rm. From this we can find the value of R3, that is RT minus R3 is equal to RT minus Rm minus R4. Next, similarly, when the switch is at position 2, the multiplier resistance is R2 plus R3 plus R4. So here also we can say that circuit will look like in this way. So when this, here we have V2, this is R2, R3 and R4, this is V2. This is Rm. So our total resistance is equal to R2, R3 plus R4 plus Rm. From this we can write R2 as RT minus 3 minus R4 minus Rm. Also we can write the total resistance is equal to R is equal to V by I. So in this way, for position 1 also, the additional resistance which comes into picture is R1. So equation will be R1 plus R2 plus R3 plus R4 is equal to RT minus Rm. So this is the equation for R1. Let us solve one example based on this. Basic D are symbol movement with an internal resistance of 50 ohms. So Rm is equal to 50 ohms and a full scale deflection current of 2 milliamperes. So Im is equal to 2 is to be used as multi-range voltmeter. Design the series string of multiplier to obtain voltage ranges of 0 to 10, 0 to 50, 0 to 100 volts and 0 to 500 volts. So here these are the values of V1, V2, V3 and V4. So we have 4 different resistors R1, R2, R3 and R4 which need to be connected in series with the meter. By using the same equations we can solve this problem. So when the switch is at position 4, so total resistance which comes into RT can be written as, so R4 can be written as RT minus Rm. So this is equal to, so if we solve for this, RT is equal to V4 by Im. V4 value we have 10 divided by Im is equal to 2, 10 power minus 3. So this is 5 into 10 power 3 ohms. So this is the total resistance, 5 into 10 power 3 minus Rm. So this is 50. So this is 5000 minus 50. So this is R4. So it comes out to be, next when the switch is at position 3, the second voltage range is V3 and so V3 is equal to 50, 50. Then Im will remain the same, 2 milliamperes. Multiplier resistance is R3 plus R4. So just if we substitute this, we'll find the total resistance. Or in this formula also we can write R3 plus R4 is equal to RT is V3 by Im minus Rm. We have the value of V3, Im and Rm. With this we can find out R3 and R4. We already have the value of R4. So whatever the value we are getting, from that we can subtract this R3 value. So R3, we have the value of R4. So if you subtract from this R4 value, we'll get the value of R3. So it comes out to be as 20 kilo ohms. Next, when the switch is at position 2, V2 is equal to 100 volts. So multiplier resistance will be R2, R3 and R4 in series. So we can write the equation as R2 plus R3 plus R4 is equal to RT minus Rm. So here RT is equal to V2 by Im minus Rm. We have the value of V2 as 100, Im is equal to 2 milliamperes and Rm is equal to 50 ohms. We'll get this. We have the value of R3, R4. From this we can find out the value of R2. It comes out to be as 25 kilo ohms. Next is At position 1, the multiplier resistance is this much. So we can write the equation in terms of, so R1 plus R2 plus R3 plus R4 is equal to V1 by Im minus Rm. So we have the value of V1. V1 is equal to 500. It is given in the question. V1 is equal to 500. So here one thing we have to remember. So more the voltage range we require, more the resistance we need to insert. So maximum resistance, maximum voltage means maximum resistance has to be there. So therefore this resistance V1 is equal to 500 by Im is equal to, that is given as 2 milliamperes, and this one is 50. We have the value of R2, R3 and R4. From this we can find out the value of R1. So in this way we can solve the problems based on for practical multi-range voltmeter. We can also use this formula, voltmeter sensitivity. So we can define sensitivity of the voltmeter as S. So it is denoted by S. It is defined as S is equal to 1 by full scale deflection current. So that is S is equal to 1 by Im, or Im we can also write it as IFS. So this is the full scale deflection current. The units for this is our ohms per volt. We can also define this as voltmeter sensitivity as the total resistance divided by the voltage. So therefore, total resistance, for the previous formula, total resistance can be written as in terms of S into V. So RSC can be written as S into V minus Rm. So we'll solve same problem can be solved in terms of sense by using this sensitivity of the voltmeter. Calculate the value of the multiplier resistance on 500 volt range of DC voltmeter that uses 50 microampere meter movement with an internal resistance of 200 ohms. So here sensitivity of the meter S is equal to 1 by Im. 1 by Im is equal to 50 into 10 power minus 6 meter movement. This is a full scale deflection current. So this is equal to 20,000 ohms. So from this we can find out the RSC is equal to S into RSC formula. We have S is equal to V by Im minus Rm. So instead of 1 by Im, we can write it as S into V minus Rm. So S value we have, then V value, V is equal to 500, that is given here, and Rm is equal to 200, internal resistance 200. With this we get the multiplier resistance as 9.99 mega ohms. Next, one more problem we can solve based on this. A meter A has a range of 0 to 100 volts and multiplier resistance of 25 kilo ohms. Meter B has a range of 0 to 1000 volts and a multiplier resistance of 150 kilo ohms. Both the meters have basic meter resistance of 1 kilo ohms. Which meter is more sensitive? So in order to find out this, so first let us see. First, there are two meters A and B. So its range is 0 to 100. So here V is equal to 100 and multiplier resistance is 25 kilo ohms, that is given. Then meter resistance is also given. Then with this formula, RSC is equal to S into V minus Rm. Find out the sensitivity of the meter A. So this is for meter A sensitivity. For meter B, RSC is given, series multiplier 150 kilo ohms, Rm is equal to 1 kilo ohms, and V is equal to 1000 volts. So its range is 1000 volts. By using this formula, again find out this value. So S is, it comes out to be as 151 ohms per volt. So this is for meter B. So comparing these two, you can say that the meter A is more sensitive as compared to, so this value is higher than this one. So meter A is more sensitive than meter B. Next, one more problem. A basic D-Arsenal movement with an internal resistance of 50 ohms, that is Rm, full scale deflection current of 2 milliamperes, that is Im, is to be used as multi-range voltmeter. Design the series string of multiplier to obtain the voltage ranges of V1 is 500, V2 is 100, V3 is 50 and V4 is 10. We have the formula RSC is equal to V by IM minus RM. So RSC1 will be V1. So more the value, here we have to remember the point, more the value of the voltage range which is to be required, the more the value of resistance. Resistance should be higher, R should be higher. So maximum value of resistance means R1, R2, R3 and R2, R3 and R4. So here you will get the value of V1 in series with the meter. So maximum voltage means maximum resistance. So find out. So V1 will be equal to, we can write this as S into IM. RSC is equal to S into IM minus RM. So here S is equal to, can write this equation as this equation, S into V1 minus RM. So S is equal to, we have the value of S as 500 into V4. V4 is equal to is 4.95 kilo ohms. So this is R4, RSC 4. Next R3 is equal to S into V3 minus R4 plus RM. So S is equal to 500, V3 is equal to 50, R4 is 50, R4 is equal to 50 and RM is equal to 4.95 kilo ohms. So substitute the value, you will get 20 kilo ohms. Next R2 is equal to S into V2. So here V3 is equal to 50, V2 is equal to 100 and V1 is equal to 500. So here V4 is equal to, this is V4 is equal to 10. So S into V2 minus R3, R4 and RM. So this is RM and this is R4 and R3 value. Substitute, you will get the value of 25 kilo ohms. Next R1 is equal to S into V1 minus R2 plus R3 plus R4 plus RM, which is equal to 500 into 500 minus. Substitute the value of, all the values are given, RM, R4, R3 and R2. We'll get it as 200 kilo ohms. So with this, I would like to thank you. So thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.